All right, so today we're going to be talking about distances and neighbors. And ultimately what we're going to get to later today is we're going to talk about product recommendation. Like if you're on Amazon and you look at an item and there's like, here's another item you might want to buy, we're going to get to that by the end of today. But first we need to talk about some more fundamental concepts. So I'm going to load up the cities data set that I may have shown you maybe on the first lecture. Doesn't really matter too much anyways, a bunch of US cities. I just wanted something kind of geometrical for us to talk about here. And so here I've highlighted two cities with these black dots. And what we can do is ask about the distance between them. And so I'm using this kind of geographical data set to start with. Yes, this is the US, I should have mentioned. Starting with this kind of geographical data set where distance literally means distance. So I could take this point represented by long and lat and take this point represented by long and lat. And I could take the distance between them and I would get some distance. Well, I would have to convert from the units of longitude and latitude to kilometers, and maybe if I was doing it properly, take into account the curvature of the Earth. But if we didn't need to worry about all that, we just want to take the distance between these two things. We have something at coordinates minus 8231, something else at coordinates minus 9242. And the way we're used to computing distance between things is to subtract them, square them, add up, and take the square root. So this is called the Euclidean distance, or I guess it's kind of like the Pythagorean distance, whatever you want to call it. It's the square root of the sum of the squares of the two distances and two coordinates. So these are 15 apart in these meaningless lat long units, but we could convert that into kilometers. And so this is called Euclidean distance. It's kind of the standard distance between two places that we're used to from regular life. And scikit-learn actually has a Euclidean distances. I think I imported it above. I think it's like what? Is that it? Okay, yeah, so scikit-learn metrics is something we used before for like mean squared error and whatnot, R-squared. But here we're doing it in a very different way. We're not talking about metrics in terms of an accuracy of how good are our predictions versus the training targets. We're not doing in supervised learning at all right now. We're just saying what is the distance between 2 points? And it's 15. And the scikit-learn Euclidean distance gives you all the pairwise distances. So here the distance between city 1 and itself is 0, between city 1 and city 2 is 15, between city 2 and city 1 is also 15 because the distance from A to B is the same as the distance from B to A, and the distance between city 2 and itself is 0. But if I gave it 5 cities, it would give me all the pairs of all the distances, which we're going to make use of in a minute. And so the next thing we're going to talk about is finding the nearest neighbor. And where this is going is when we talk about product recommendation later today, we're going to say which items are the nearest items to the item you're looking at. And those neighbors, those close by items on Amazon, can be ones that we could recommend because they would be considered similar. So that's where we're going. So can we find the closest cities to city 0? Okay, well, I can call this pairwise Euclidean distance thing. And I can just take the first 4. And now we have distance between, and now I'm getting my indexes messed up, if it's city 0 or city 1, we'll call it city 0. So this is city 0 with itself, city 0 with city 1, city 0 with city 2, city 0 with city 3, and so on and so forth. Cities 1 with city 0, which is the same as 0 with 1. We have a symmetry of this matrix, and 1 with 2, and so on and so forth. And the actual matrix is a lot bigger. I just took the first 4 of it. Okay, so we have this 4x4 matrix. And if I take the first row of that matrix, now I have the distances between city 0 and all the other cities. And so right now, again, I just took the first 4 cities so we could look at it. But if I did that for all the cities, I would now have the distance between city 0 and all the cities. And if I took the smallest distance, that would tell me which city was closest to city 0. And so argmin and numpy, well, I should guess first there's just regular min in numpy, which just gives you the smallest value, in this case 0, the distance to itself. Argmin, I forget if you've seen this before, but instead of it giving you the smallest element in a list or an array, it gives you the index of the smallest element. So if this was the smallest, it would return 2 because this is in position 2. If this was the smallest, it would return 3 because this is in position 3. Here it's returning 0 because this is the smallest distance in position 0. And that's kind of useless because, well, as humans, we know when you say which city is the closest to city 0, we're not including itself. Sure, it is the closest to itself, but that's kind of silly. So what I'm going to do is I'm just going to use this fill diagonal thing in NumPy, and it's going to replace everything on the diagonal here with infinity. And my purpose for doing that is, well, now when I ask what is the smallest thing here, it's definitely not going to pick infinity because infinity is the biggest thing you can stick into Python. And so now when I ask for the smallest, it's just going to give me the next smallest. Another thing I could have done is I could have just excluded this and found and looked in the rest of the list, but that would be a bit more of a hassle in terms of keeping track of the indices. And so this is kind of easier. So if I stick these infinities in the diagonal and then I ask for row 0, which is to say the distances from city 0 to other cities, which is the smallest, I now get a real answer out of it, which is apparently 1. So apparently city 1 is the closest city to city 0. And we could do this with all the cities included to get the closest overall. Right now I was only looking within the first 4, but if we did it with all of them, we would get the closest overall. Any questions or comments on what we've talked about so far? Okay, so everything is silent except for my computer fan, which is going crazy. Not sure if you can hear it. Let me move the microphone a bit away from it. Okay, why 0 is 0 and sometimes it is 10 to the minus, yeah. That has to do with floating point issues, which we don't really talk about in this course at all. The short answer is that all the numbers in a computer are just represented approximately. And so everything is kind of slightly rounded in a computer. And so sometimes instead of 0, you'll get an extremely small number like 10 to the minus 13. And it has to do with things not being perfectly represented. Yes, that's right. Yeah, that is true. It is a nuisance, but it's not really going to affect us today, so we can just move on. I'm going to run this, and I now get the distance between well, I've just subsetted the first 10 here. So between the first 10 cities and the point 0, 0, and I can take the argument of this, and that's going to tell me that apparently city number 357 is the closest to 0.00, which was somewhere on the map. And so what I want you to get from here is thinking about distances between some new kind of query item and all the items we have in the data set, and the kind of scikit-learn functions to do this, and the numpy functions to do this. By the way, I should have said, what we're doing today is not supervised learning. What we've been doing in the entire course pretty much is supervised learning. Like you have X and Y and learn to predict Y from X. And what we're doing today is part of what's called unsupervised learning, which is where we're not trying to predict something, but we're trying to do some other task. In this case, we're trying to find a nearest neighbor, and we'll talk a little more unsupervised learning later in the course as well. So do you have some best practice on where to locate 0, 0? I'm not, there's no method to what I'm doing here. I just picked this arbitrarily. I'm just trying to show you the syntax, but there's nothing to read into my choice of 0, 0 or anything like that. I'm only trying to demonstrate what we can do with these functions and to get you thinking about distances. And so the next thing I want to do is use a scikit-learn object called nearest neighbors to do the heavy lifting for us, to do what we just did, basically. And so this is kind of something new that we haven't seen before in scikit-learn. It's not a transformer, it's not a estimator, it's not a, yeah, it's just a kind of a new thing in scikit-learn. It still has fit, and the way it works is you make a nearest neighbors object and you tell it how many neighbors you want. So what that means is if n neighbors is 1, it means I give it a point, it's going to give me the 1 closest neighbor. If n neighbors was 3, then if I gave it a point, it would give me the 3 closest neighbors. And it's going to be using Euclidean distance by default, just like we were using above. We were using Euclidean distances. This nearest neighbors in scikit-learn is also using Euclidean distances by default, although we're going to change that later today. Yeah, good point in the chat. N neighbors equals 1 will return itself if the point you're querying is in the data set. In this case, the point I'm querying is 0, 0. 0, 0 was not in the data set of cities, and so it will not return itself because itself is not actually in there. Any other questions? Okay, so, right. So this is, we can find the closest city in the training set, and this is exactly what you're talking about in the chat, that the closest city to city 0 is just city 0, and the distance is 0. Oh, by the way, I should address the junk coming out of this. What is this? So many parentheses here. Let me change, okay, let me address that down here. So, okay, I'll answer those questions in a second. I just have some things on the stack I want to get through. Okay, I'm going to change number of neighbors to 2. I'm going to call it. So here's what's happening. It's saying that the closest city is itself with a distance of 0, and the next closest is city 1 with a distance of 0.25. Now I want to show you the documentation for a second. This is not documentation that I want. Okay. Okay. So, come on, write things to me. There, this is what I want. Okay, so the function we were calling is called kneighbours. And what I want to show you in the documentation is that it tells you it's returning 2 things. For those of you who haven't done much Python, you might not have seen this before. It's basically returning a tuple of these 2 things. And you can see it's the neighbor distances and the neighbor indices that is being returned. And so if we want to capture those, we can actually capture, I'll call it distances. So in Python, when you call a function that returns 2 things, you can unpack the stuff right here on the equal sign. What's actually happening is returning a tuple and you're unpacking the tuple, but I just want to show you. Okay, so now the kind of weird looking output seems a little bit better. And so going back to the documentation, yeah, it returns an array of shape n queries by n neighbors. So each of these is of size n queries by n neighbors. In this case, we're only querying 1 thing. So we're only asking what's the nearest neighbor to this first city, but we could ask it in parallel. Just like in scikit-learn, you can call predict on like 10 things at the same time, and it'll give you the 10 predictions. You can call kneighbors on 10 things at the same time, and it'll give you the neighbors for those 10 things. And so that's this dimension of 1. And then the dimension of 2 here is how many neighbors you actually ask for. And so if you give it 10 things and ask for 5 neighbors of each, it'll give you a 10 by 5 matrix. And so now we've kind of unpacked the unwieldy looking weird thing coming out of here with so many parentheses and brackets. Okay, let me take some questions now. What does fit do? Yeah, so it may do something fancy that you might learn about in a like algorithms and data structures course, like make some sort of KD tree or something that's way beyond our scope here. And so for our purposes, you can consider that it just does nothing, or you can consider that it actually computes the distances. I don't know if it actually computes the distances and stores them or not. But yeah, we don't really need to worry about that. Is neighbors returning only based on one parameter here? What if we have a temporal element? That's to say we have 2 parameters. Okay, so I think I know what that question is asking, but let me leave that for a minute because I think it may get answered in what I'm about to say next, which is namely, all this was in 2 dimensions. So every city there had a lat and a long, an x and a y coordinate. So when we take distance, it was like point over here, what's the distance? But we can generalize this, extend this to not just points in physical 2-dimensional space or physical 3-dimensional space, but just any 2 vectors. And so what I'm going to do here, and a vector is just a list of numbers, if you've not taken a linear algebra course or seen that before, we can think of it as just a list of numbers. So what I'm going to do here is I'm going to load this housing data. I know this is like really sloppy and I keep copying and pasting the code, and I should just move it to a file, and yeah, not my highest priority in life right now, so I'm just going to copy and paste and set a bad example. Okay, so you remember this housing stuff. We've looked at this many times by now. And what I could do is I could say, you know what? Each of these houses is just a list of numbers. It is a bunch of these features, these columns. And so I could do what we've been doing all this time. I could find the distance between 2 houses. I could say which house is similar to which other house based on these features you have. And you would take the vector like this for one house, and you take the vector like this for another house, and it would just do those things we talked about. I would subtract them, square, sum, and square root. That's the Euclidean distance. So the Euclidean distance in our life is like usually a 2 or 3-dimensional thing, but mathematically, you can take the distance between any 2 vectors, even if they are containing, as you can see here, 292 numbers long, whereas with the cities, it was just 2 numbers long, an x coordinate and a y coordinate. But we could take this giant thing of 292 numbers, take another giant thing of 292 numbers, and say, what is the distance between them? And it's no longer distance in the sense of physical, geometrical, geographical space, but it's mathematically the exact same operation. And if these 2 vectors are similar, it's going to have a low distance. And if you ask for the nearest neighbor in terms of house, okay, pun not intended there. It's not like who's your neighbor, what's the house next door. It's the neighbor in terms of what house in the data set has the smallest distance to the query house. And so here's some Euclidean distances between houses, for example, the first 3 in our housing data set. And so we could say, you know, the distance between house 1 and house 2 is this. And this has no meaningful units to me whatsoever, because this is just a mush of summing and squaring all these weird things which were already scaled and encoded and whatever. So by this point for me, this is just a number. And smaller means more similar, and I'm not going to read into it more than that. But we can use the same scikit-learn thing before. So for example, we can call this, like, create the scikit-learn nearest neighbors object, nearest neighbors 1, put in the training set as our data set, as our fit. That is to say, when we search, we're going to search through houses in the training set, and then we can give it the first house in the test set and say, hey, which house in the training set is most similar to the house in the test set? And here, like, the fact that there's train and test might be irrelevant to what you're doing. It depends on what you're even trying to accomplish by doing this in the first place. possibly more likely you don't have a training set and a test set and you're just interested in what houses are similar to what others, but this was convenient for me to show you because I can take a query house that was not even in the original data set. So here you have it. Apparently, the closest house to test example number 1 is training example number 135 with a meaningless distance of 6.5. And so that's does that answer your question in the chat, Ali, in terms of not really. Okay. Do you want to elaborate on your question?
Yeah, sure. So like kind of my question is, let's say there is a temporal element to what we are looking at, and there are some neighbors and clustering happening in real time. But like it is hard to kind of like get the nearest one when you have that temporal thing going on. So like let's say there is something popping up at the later time when you did your nearest neighbor analysis on this point, but like it is there are still coming, like there are points that are still coming. So like my question is coming from the point of view that I wanted to parallelize the computation of this kind of nearest neighbor, but it is kind of difficult when we have that temporal effect.
Okay, I think it sounds pretty far out of the scope for today. So why don't we follow up with that on
Sure.
Piazza or in office hours?
Yep, sure. Thanks.
No worries. Okay. Um, okay, so now I'm just doing the same thing, except I'm going to ask it for the 5 nearest neighbors instead of 1. And so here, oh right, I did this on purpose. I put this error here because this error happens to me all the time, and it's very annoying and mysterious and says something about reshaping. And the reason that this happens is that this is just, you may have seen this error with like dot predict and scikit-learn. If you call dot predict and scikit-learn with like this exact same error happens, and the problem is the difference between the single square bracket and the double square bracket. So basically, if the thing you're trying to predict on or find the neighbors on is a one-dimensional array, then scikit-learn gets upset because it always wants a two-dimensional array. It wants you to make it 1 by 292 so that it's clear that it's one example and 292 features rather than this supposedly ambiguous thing. So you may have encountered the same type of thing with any of the stuff we've talked about with dot predict. If you try to dot predict on just a single example, you may have seen, I think the other way around this is to put a :1 here. Yeah, so you may have seen me do that in some of the lectures, but you just have to be a bit careful to get it in the shape that it wants. Okay, any questions? Okay, next topic. So are there feature importances in this? Not really. Yeah, I guess, I mean, the only analog to feature importances that I can really say here is that if you didn't rescale your features, then the ones that have huge values would tend to be the most significant when you're computing distances. And like if you had like a location where one axis was in meters and one was in kilometers, the one in meters would kind of dominate. But like it is generally advisable to scale when you do this kind of thing, and I did scale, and so it kind of puts all the features on equal footing. And I guess my short answer to your question is no, because we're not really trying to predict anything. Okay, so yeah, we've talked all about Euclidean distance, but one of the main themes that we're going to get to today is that sometimes Euclidean distance is not the best. And there's this other thing called cosine similarity that is very popular in a lot of applications, and you're going to be seeing it today and Tuesday and in homework 6. And I'm going to try to convince you why you might care about cosine similarity and that Euclidean distance is not the only thing you ever care about. So I already have this open anyway. So you can see this metric option when you make one of these nearest neighbors objects. And so by default, it's Euclidean distance, but there's a bunch of options you can give it, and we're going to set it to the cosine similarity in a minute. So the cosine similarity is defined as the cosine of the angle between two vectors. And so if the angle is small, they're considered more similar. If the angle is large, they're considered more different. Let me show you. This is not really the picture. There's a good picture I want to show you, but it's coming later, so we'll just leave it for now. So what we're going to be thinking of is that each of these cities or houses is going to be a vector that starts from 0 and points in some direction. So I think there's a missed opportunity here that okay, let me scroll back up to the city and try to salvage this. Because I just thought of a way that I think will make it more clear. Okay, so, right. Okay, so somewhere on here is the point 0, 0, which is actually off of the screen, but it's somewhere, say, around here. Can you see my drawing? Okay, so basically these two cities are kind of like, can be thought of as two vectors from the point 0, 0 to the two cities. And then there's going to be an angle between the two cities. And when the two cities are close to each other, that angle is going to kind of be smaller. And if you take a city that's more farther away, the angle might be bigger. Now, one thing that is, yes, theta is 0. The angle is 0 if they're the same vector. Now, one thing that is new here is that unlike Euclidean distance, this cosine similarity depends on your choice of where is 0, 0, where is the origin. Because if I called the origin somewhere else over here, then you would get different results. Whereas with Euclidean distance, there's no notion of where 0 is. It's just the distance between two things. So that's something we have to keep in mind. But for a lot of applications, there's kind of a natural 0 point, not really so much in the city one, but for example, in the housing one, the 0 point is basically is natural because we've scaled the numerical features. So everything is already kind of centered around 0 already in the housing case. And so that kind of works out pretty well. What if you have a city in New York and a city in Alaska? Wouldn't that angle be small, but the cities are in fact far? Yes, we're going to get to that. We're going to get to that. Yeah, okay, let's go back down. So I'm gonna clear this. Yeah, so for in this case, like if you had an origin maybe over here, then maybe it would do a more sensible job. But we'll talk about that in a second. So how do I get rid of this drawing thing? Okay, I'm gonna scroll. So brace yourself for the scrolling. Okay, so that's what cosine similarity is. It's you have a 0 point called the origin, and then you draw a vector, which is basically an arrow from the 0 point to whatever points you're talking about, and then you look at the angle between them. And in degrees, the angle between them would be like between 0 and 180, I guess. But the cosine of that is between -1 and 1. So when two things are kind of pointing in the exact same direction, the angle is close to 0, the cosine similarity is close to 1. And when they're pointed pretty much in the opposite direction, the angle is around 180, the cosine is -1. So this is a similarity measure rather than a distance measure, because more similar is a higher value, whereas with the Euclidean distance, more similar was a lower value, is towards 0. So we actually saw this kind of thing before with like, we had mean squared error and then R² score when we talked about regression, and they were kind of backwards of each other, like lower mean squared error was better and higher R² score was better. So it's the same kind of thing here. there's similarities and there's distances, and there's kind of opposites of each other. So we just have to keep track of that as we're going through this. Okay, so that's what we just talked about. So if you want to implement this in scikit-learn, and I'm going to show you later today why you should care about this, and this is not a waste of your time, why the cosine similarity could actually be a lot better in some cases, but we're not there yet. But here, just the implementation, if you set metric equals cosine, then it does all the same, everything exactly the same, except it's sorting by the cosine of the angle instead of the distance. Now, for the house, which was like a 200 length vector, we can't really imagine like an angle in our brains because our brains cannot visualize like an arrow in 200 dimensional space. We can only really think in the 3-dimensional space that we live in. And so for the houses, it kind of just becomes conceptual at that point. We can't draw one arrow and draw the other arrow and think about the angle exactly because they're in this higher dimensional space that the house space that's 200 dimensions. But we can still do all the calculations and it can still be useful. It's just harder for us to think about. Yeah, one thing I want, let me take questions and then I'll keep going. Okay. Just looking at the chat. What would be the value of calculating the nearest neighbor in a house data set? Like in what sense? Yeah, so I mean, maybe you're a realtor and your client says, can you, I want to sell my house, how much is it worth? And you say $1 million, and they say, well, what makes you say that? Can you show me some similar houses in the area and how much they sold for? And you can kind of eyeball it, but if your data set is too big and you have some kind of house similarity measure, you can do a query and say, hey, last 5 years sold in this geographical area, what are the kind of 5 nearest, most similar houses? And then you can pull those up and say, here you go, client. Here's some kind of comparables that you might want to look at. I don't know. Yeah, just an example. Okay. So yeah, just again, I know it's kind of boring, but I also don't want you to be confused about it. It's this issue of similarity versus distance. So when you set metric equals cosine, you can see that the closer ones have a smaller value, and that's because using cosine distance instead of cosine similarity, and that's because it just wants to do everything in terms of distances for consistency. And so it actually takes 1 minus the cosine similarity, and that's what they call in scikit-learn the cosine distance. And that way, everything's in terms of distance. So when you see this number come out of here, this number is the 1 minus the cosine similarity. So the cosine similarity here is 0.9, 0.89, because it's 1 minus this. But they're doing everything in terms of distances for consistency. So yeah, the cosine similarity in this particular case, in this case, the cosine distance that it printed out was 0.118, and the cosine similarity is 1 minus that, which is 0.88. And the smallest cosine similarity in the whole data set is this. So that is just to say, keep in mind the cosine similarity can be negative because cosine of an angle, if that angle is more than 90 degrees, it'll be negative. Okay, whew. Yes, lots to talk about. So Euclidean versus cosine distance. So one issue is that the cosine similarity relies on an origin, whereas Euclidean distance does not. But this I kind of mentioned earlier. The way we pre-processed our features, we kind of did have a kind of a reasonable origin. The 0, 0 point was just like average for all the numeric features and had none of the one-hot encoding calculations. And so often it's not that hard to treat 0 as like a natural origin point from which to draw your arrows. Because like if you just have scaled numeric features, the origin is like the average house. And it's like this house deviates from the average house in this direction. This house deviates from the average house in that direction. What's the angle? And actually kind of makes some sense to do this. So this little demo here is just to say, here's some cosine similarities. If I just shift all the house vectors by 1, which is another way of saying shift the origin, then I actually get different values. Whereas Euclidean distance, if I shift all the houses vectors by 1, then I get all the exact same values. I know it's the same thing we saw with the cities. If we move the cities around or move the origin around, all the distances are going to be the same. But for cosine, the Euclidean distances are going to be the same. But for cosine, it actually depends where the origin is with respect to your points. So these are just some drawings I drew. Yeah, so smaller angle meaning less, meaning more similar, kind of medium case, and in the larger case where the cosine similarity is actually negative because that angle is more than 90 degrees. We're very close to our break, by the way, so hang on there if you're losing me. Well, I'm going to declare that we're very close to our break. So the last thing I want to show you before the break is bring back the cilantro data set from the first week. I just thought this would be kind of fun. I mean, if you compute distances, you can basically say how similar are two students just based on these two things that they entered in, what percent of days do you eat meat and what's your expected grade in the class. And so here we can draw, this is 4 of you real people out there. I don't know who you are, probably the first 4 people who filled out the survey if you're at the top of the data set. So this is 4 of you and your kind of vectors of how you fill out the survey. And so you might say, hey, these 2 people are maybe more similar and these 2 people are more similar because they have smaller angles and also smaller Euclidean distances. Yeah, okay. I just see a question in the chat. Changing all the values shouldn't affect the actual ordering of the cosine distances. I can't guarantee that actually. It might. Even the ordering might change if you change the origin. I would have to think about it more, but that's my gut feeling. Our model is doing a very good job for the large cosine similarity, have very different predict proba and vice versa. Well, I just want to clarify, we're not doing supervised learning here. So we're not actually trying to predict anything here. I know I've brought back these data sets like the housing and the cilantro where we were trying to do supervised learning and predict something. But for today, we're only focused on finding are things close to each other. And we're dropping the whole notion of thinking about predicting the y values for today. When would we want to use cosine distance? Yeah, so I'm going to get to that by the end of today, hopefully. There's kind of a punchline coming. But let us first take our break and resume at 11:45. Today is a very full lecture and kind of a more mathematical lecture than usual, I guess. Definitely feels like we're going lightning speed. Okay, so now I'm going to introduce this data set I was alluding to, which is this data set of Amazon products. There's a whole bunch of sections you can download. I picked the patio, lawn, and garden one. I don't even remember why. But the data set looks like this. Each row is where someone rated an item on Amazon. So in this case, this user rated this item 5 stars. And we're not going to use the timestamp here. So basically what we have is a bunch of ratings. And what we're going to do is we're going to try to use this to find similar items. I should say there's a lot of ways remember with the housing, we had all the features, number of rooms, quality, size, blah, 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 blah. So for an item on Amazon, you could generate a bunch of features as well, like price, how long it's been on there, what type of thing it is, maybe some count vectorizer features from the text of the description, all those kinds of things. So you could make like really rich features for each item on Amazon and then find similar items based on those, just like we did on the housing data set. What I'm doing instead is I'm going to describe an item by the ratings it got. And so the vector for each item is going to be a vector of length number of users. That is all the ratings it got from those corresponding users. And the reason why I'm going to do it this way is it's going to illustrate an important point about sparsity that is going to come up next week and on the homework and with cosine similarity and all that kind of stuff. So that's kind of a roadmap of where we're going. So yeah, another approach would just be look at actual features of the item, but we're going to do everything based only on this ratings data. And we're going to try to find similar items based only on finding other items that were rated similarly. Okay, so we have about 1 million ratings. The average rating is around 4 stars. Here's a histogram of the number of ratings per item. So most items got less than 100 ratings, but then there's some long tail of kind of super items. So some item has 3,000 ratings apparently. And we can do a histogram for users, and it's a similar kind of thing. So most users have only rated a small number of items, but there's some user apparently that has rated 150 items. So that's pretty hardcore, good for them. Okay, so here's the plan. We are going to create a table, a data frame, a matrix, whatever you want to call it, of each row is an item and each column is a user. And we're going to stick in the corresponding rating if there is one available when that user rated that item. And so our feature vector for each item is going to be all the users. And what I want to talk about, we have to make a little detour before we get to the punchline, is how big is this matrix going to be? Well, we have about 100,000 items and 700,000 users. And so I need to make a data frame or table, whatever you want to call it, of size 100,000 rows by 700,000 columns or features. And in terms of how big that would be about 600 gigabytes on my computer, which is not going to fit. So I'm bringing back this Bitmoji that we had from a while ago. So this is not going to fit on my computer, this giant matrix of all the users and all the items. And so we need to do something about this. By the way, another case where this could happen is if you want to make word features using count vectorizer. So if you want to look at the description of the items and use count vectorizer, and you had like 1 million possible words you were looking at, you would get the exact same thing. You'd have like 100,000 items by 1 million words from count vectorizer, and you could get kind of the same problem. So is there hope? Yeah, so here's why there's hope. If we were to create such a table, it would be mostly zeros. And the reason for that is those histograms that we saw earlier. So we saw that actually most users only rated a few items, like maybe 5 or something, or 1. And so for a particular item, there's not going to be a rating for most users. A particular item will only have been rated by a small number of users. And in particular, we have 1 million ratings, but this is the number of possible ratings. If every single person rated every single item, then the number of ratings would be the number of users times the number of items, which is 76 billion. Okay, so out of 76 billion possible ratings, possible user item pairs, only 1 million of those actually materialized. And so if we were to make that big table, then it would be 99.999% missing data, basically, which we are going to represent as 0 here in this case. So I should have said that. That's important. Is there hope? Okay. So if the lack of a rating is being represented as a 0, then this humongous table we're making is actually mostly zeros. And again, you could have the same thing with count vectorizer. If you had count vectorizer with a ton of words that you cared about and a ton of training examples, you would get this massive table that might blow up your computer, but it has this same silver lining that most words will not appear in most item descriptions, and so you're going to get a lot of 0 word counts. It's completely analogous. Okay. Any questions about this that we just talked about? What are products that actually have a 0 rating? I think the only possible ratings are 1 star through 5 stars, so we're okay there. Although I'm sure some people would like to give 0 stars to some items. Okay, so here is the thing. There is this thing called sparse matrix, which is like a data type in Python, like a list or a pandas data frame or a NumPy array. There's this other thing called a sparse matrix that will exist outside of Python too, but we're using Python. And it is going to rescue us. It is going to allow us to store ginormous tables in which most of the things in there are 0. And at a high level overview, the trick it's going to do is it's only going to store the non-zero elements. And so it's going to say, well, there's a, and how it works under the hood is not that critical for our purposes in this course. But what I really want you to know for our purposes in this course is that there's a way of doing this, and it's called a sparse matrix. And it is a specialized data structure or specialized data type for cases where you have a giant array and almost everything in it is 0. And so I'm actually loading in these IMDb reviews we saw from a while ago, and I'm doing count vectorizer on them because we've used count vectorizer a lot in the course to get ourselves word counts. But when I actually call transform or fit transform and I get these counts, I don't think we actually ever addressed the type of the output is actually one of these sparse matrices. So I've been saying all this time, well, count vectorizer is another example where you have lots of zeros and you're going to get this massive array, but it never blew up our computers a month or two ago. And the reason for that is that without me really pointing it out to you, scikit-learn was actually automatically returning this sparse matrix type that is only storing the non-zeros. Again, that's the trick it plays. Because if you recall, do I not have the... okay, wait, I think this is worth just quickly running back to lecture 4, take a 1-minute detour, and I think it'll be worthwhile. We made these tables in lecture 4, right? So this is what I want to show. This is mostly zeros because most reviews don't have all the possible words in them. And so it was actually making a sparse matrix without telling us. And when I printed it for you, I actually did this to array without telling you what I was doing, which turned it from a sparse matrix type into a regular type, array type, just so I could show it to you. And then I kind of swept it under the rug. In this case, it didn't blow up my computer because I just had a tiny, relatively tiny data set, 10,000 reviews and 1,000 words. But what we're talking about here is 100,000 items and 1 million users, and that's way too much. It's going to blow up our computer. But we would have a table like this with a lot of zeros and a couple 1 stars, 2 stars, 3 stars, 4 stars, 5 stars. So my point in showing you that was just to say, you have been dealing with the sparse matrix data type without even knowing it, because that's what comes out of count vectorizer. And so when you try to print it out, it doesn't actually print it out. That's why I had to do the to array thing. And so, yeah, I don't want to go too much into the under the hood of this in Python, but just be aware of what type you're dealing with. And like, I could talk for an hour just about this topic. And in fact, I kind of do in one of my MDS courses. But there's a lot to this sparse matrix thing that is not really of interest to us here. But what is of interest to us here is basically just asking yourself, well, what fraction of the entries are 0 or non-zero? And if in this case, it's only like 0.2% non-zero. In our user item case, it's even more extreme. It was like 0.001% non-zero. The more zeros you have, the better idea this is, because it's not storing all those zeros when it's in the sparse matrix type. As soon as you convert this to a regular NumPy array, I got rid of this too soon. As soon as you return this to a regular NumPy array, your computer is literally storing 0, 0, 0, 0, and that takes up memory, and then you run out of memory. And so that's basically what the good thing is about the sparse matrix. So it only stores non-zero elements. It actually stores the location, like at location 5, 192, there's a 3, and it's super helpful that way. By the way, there was kind of that hilarious incident in one of our lectures with the one-hot encoder. So the same thing with the one-hot encoder. If you're wondering what is this that I keep setting sparse equals false, sparse equals false. So one-hot encoder, like count vectorizer, by default also returns the sparse matrix data type in Python. And that's because you also have a bunch of zeros with one-hot encoder. Like if you have 100 categories, well, one-hot encoder, only one of them is a 1, all the rest are zeros. And so you're going to have lots and lots of zeros. When if you have categorical variables with many categories, you're going to make many columns, mostly full of zeros. And so when you have those types of variables, you might also want to use a sparse matrix with one-hot encoder. And that's actually what it does by default. And I kept doing sparse equals false just because it was easier for me to show you what was coming out. But in reality, we can just leave it the default as sparse equals true. And you'll just have these sparse matrices coming out of one-hot encoder. You'll have these sparse matrices coming out of count vectorizer. And the people who made scikit-learn figured it all out, so you don't have to worry about it. You got a pipeline, it comes out of count vectorizer, goes into logistic regression. Logistic regression knows how to handle a sparse matrix coming in. Comes out of one-hot encoder, goes into column transformer, goes into wherever. It's all kind of handled under the hood. So it's important that you know this exists, but it's not super important to go into the details. Yeah, but it's important to know that there exists. If you have a ginormous thing, mostly full of zeros, there's a way to store it more efficiently. And furthermore, scikit-learn has been doing this to you without even telling you, and everything just worked. So this next section I have, I'm going to skip because if I do it, we'll run out of time today. And it's kind of outside the scope of the course, but I put it here because there's some gotchas that are really frustrating. If you ever work with this in more detail, you may want to refer back to these notes that I'm leaving here for you, because there are some things that you might get some cryptic errors, and then check the type of the thing and realize the sparse matrix, and maybe you'll come back to this and realize what was happening. But it's not worth our time right now, given the time limitations. So I'll just leave that for you to read over later, and we'll get back to what we were trying to do. Any questions before we move on, though? Okay, no questions. I know this is a bit mundane. Let's get back to the exciting data set. Okay, so all I'm really trying to say is with this data set, I can now make this ginormous matrix that we just talked about, that is 1 million users by 100,000 items, which would never actually fit on my computer because I don't have 600 gigabytes of memory. I have 16 gigs of RAM on this laptop. But I can make this thing in Python that is the sparse matrix type that contains that information, just stored in a very efficient way by not storing all the zeros explicitly. So now that I have that, I can ask for its shape, number of users by number of items. I think I actually want number of items by number of users, so I'm going to transpose this in a minute. But and this is how many non-zeros it has. It has 100,000 non-zeros, sorry, 900,000 non-zeros, which is exactly the number of ratings, because every time you have a rating somewhere, that's one of these non-zero elements. User number 5, rated item number 22 with 3 stars, so now you have a 3 in there. And so the number of non-zeros is the number of ratings. Any questions about that? I think for my future self, I would rather add in a diagram of this. I think that would be helpful. Okay, so yeah, we can do all kinds of exploratory data analysis. We can say, let's find the item. Okay, let's find the item with the most reviews, and we can yeah, regular NumPy operations work on this sparse matrix data type. And so apparently the item with the most reviews, we saw that in the histogram, it had around 3,000 reviews, and this is the item ID, whatever. And I set things up above up here. I didn't go through this mess, but long story short, I set things up for you so that I can actually get it to print out the URL. And so I think this is really cool because you're messing around in Jupyter and you calculate, find me the item with whatever, and then you can just get it to print out the URL and you can actually click the URL. And this is it. So there you go. This was the item with the most ratings in the dataset. And you can see the dataset's kind of old because this now has 16,800 ratings, whereas in the dataset it only had 3,000 ratings. The dataset was maybe collected like 5 years ago or more, I'm not sure. But in that data set of the patio, lawn and garden section, we asked it for the item with the most ratings and it gave us this, and that was kind of cool. And so going back now to product similarity, which was like our goal at the beginning of today, let's see, frequently bought together, is it recommending me? Recommendations, cool. So as you know, Amazon tries to sell us extra stuff, and we're gonna take a simplistic approach to that and say, let's just find similar items by using nearest neighbors like we talked about earlier today. And so we're going to focus on this grill cleaning brush. Well, I heard these are sometimes problematic. This one looks more safe though, so that's good. Anyways, we're going to focus on this grill cleaning brush. And what we're going to do is try to find similar items to it using the nearest neighbor stuff we talked about earlier. Okay, so here's our grill brush. We're going to take this, okay, the .t is transposed, just turn it on its side. So instead of the user item matrix, I want the item user matrix. And so now, now I have a matrix whose rows are my 100,000 items and whose columns are my 700,000 users. And I'm just going to throw this right into scikit-learn nearest neighbors. And so first with cities, we had 2 dimensions. Then with houses, we had 292 dimensions. Now we're finding distances and neighbors in a 714,000 dimensional world that we clearly cannot visualize. But each item is a point or a vector in this 700,000 dimensional space because each column is a user. And so each item is the ratings for every possible user. So the vector for this grill brush, I should have actually printed it out. Here it is. Press page down by accident. Sparse matrix. Let me make it a regular matrix. Okay, so the vector for this grill brush is like 0, 0, 0, but then if user number 4 gave it 5 stars, say it would have a 5 here. So it might be like 0, 0, 0, 5, 0, 0, 0, 0, 0, 2, 0, 0, 0, 0, 1. And so all the zeros mean that user didn't rate this item, but when you have a 1, 2, 3, 4, or 5, that's the number of stars that that particular user gave to the item. And so then I can just throw this into nearest neighbors like we talked about earlier and say, find me similar items by comparing these rows and find me another item that is similar in the sense that similar users rated it similarly, because that's what these vectors now mean. They mean all the ratings from all the users. So the analog for word counts would be like, find me similar items in the sense that it contains similar words. But here we're using the user ratings instead to get our similarity. Okay, so here is the nearest neighbors according to scikit-learn. We passed in the whole data set. We gave it as the query item our grill brush, this thing. And here are the 6 things that it returned that are nearest. And the first one is the grill brush itself because it was in the data set. And then these are the next 5 nearest neighbors. Right, so these are the next 5 nearest neighbors that it considered close to the grill brush. And we can get it to print out these URLs and we can actually click on these things. So this is apparently similar to the grill brush. I mean, you tell me if it's similar. It's also by Mr. Grill. It's by the same grill hogs. And remember, this similarity is being computed entirely by the same users on Amazon rated these things similarly. It has nothing to do with the text or the price or the brand or anything. It's just looking at who rated this item and who rated this item. And apparently there's a bunch of reviewers in common, and that's calling it to be similar. So yeah, I find this fun to play around with because you can click on stuff. Actually, this one looks a little skeptical. I'm a bit skeptical of. This one doesn't even exist anymore, and so on and so forth. So someone says in the chat, that seems like a strange measure of similarity to me. I mean, if it were me, I'd probably try to combine all these things. I'd try to combine the other features I talked about, like the price, the category, the text, but maybe I would look at the users as well, because it could give us useful information about similarity. I doubt this is how Amazon is doing it, though. But for example, actually, I mean, it does say customers also viewed, which is pretty much exactly what we're doing right now, except we're looking at actual ratings instead of only views. But if you look at views instead of ratings, this is literally what we're doing. It's asking, find me similar items in the sense that there are a bunch of people who viewed both of them. That's actually pretty much what we're doing, except with ratings instead of views. So I think it's not that crazy. I mean, we're actually looking at the number of stars as well, but we don't have to do that. We could just be making it binary, just like did the user rate it or not, and stick a 1 there if they did and a 0 if they didn't, and forget about the number of stars. And I'm pretty sure we'd get quite similar results. Okay. So, yeah. Okay, so what this is saying here is that according to this data set, this is old, but according to this data set, oh, sorry, I said 3,000. Oh yeah, never mind. Yeah, so the grill brush now it has 800 ratings, but at the time the data set was collected, it had 272 ratings. And with the nearest neighbor, it had 37 raters in common. With the next neighbor, it had 28 raters in common. And with the last 3, it only had 1 rater in common. So very tenuous connections with neighbors number 3, 4, and 5. And so, yeah, and at that point, I would say it's not really doing anything interesting. And probably having it be by customers viewed instead of customers rated makes a lot of sense, because you have way more data that way. I mean, a person views, well, personally, I view like at least probably 100 times more things than I rate. I view a lot of things, I buy some things, I rate hardly anything. And so with views, you would have a much richer data set than ratings. And I think it makes a lot of sense that they're doing that. And maybe I should look for a data set like that. Okay, questions? Okay, so we have 10 minutes left to do the trickiest part of the lecture. This is very complicated, what I'm about to talk about, and it's okay if it doesn't completely sink in by the end of today. This is kind of one of the more conceptually complicated notions in the course, but I think it's really cool to talk about. So I'm gonna give it my best shot in the next 10 minutes. And okay, here we go. So I'm going to make a little toy data set with 2 users, Alice and Bob. And I'm going to have 2 items in my data set. So I'm considering a mini Amazon that's only selling item 1 and item 2. And then I have this query item. And I want to know, based on this, which item should I recommend? Which one is more similar to the query item? Is it item 1 or item 2? I don't know if anyone has any thoughts. Anyone? Item 1? Okay. Huh? People are saying item 1. Okay. 2, yeah. Well, okay. My original thought was, if I was just looking at this, I was going to say item 2 because at least Alice liked both of these. However, you could pick Yeah, whereas Bob didn't actually rate the query item, so we don't really know about Bob. So I was just looking at Alice, but it's obviously subjective. I mean, there's no exact answer here. But what I want to do is plot them as vectors, because all this cosine stuff was about vectors. So here's Alice's rating in stars. Here's Bob's rating in stars on the y-axis. Here's item 1, here's item 2, and here's the query item. And I think this geometrical, I'm bringing it back down to 2 dimensions so we can draw it. So in order to do that, I had to make there be only 2 users, because the number of dimensions is the number of users. Here Alice and here Bob. So I'm bringing it back down to 2 dimensions so we can draw it, and here's how it works. So in terms, now the question is, which one is closer in terms of the distance measures we talked about? And if you compute Euclidean distances, just looking at the first row here, the Euclidean distance to item 1 is 4.5, and the Euclidean distance to item 2 is 5. I couldn't get the axes like scaled properly, so it doesn't look quite right on the picture. But this distance here is 5, and this distance here is 4.5. So according to Euclidean distance, it's going to pick item 1 as the more similar item. But as you can see here, according to the angle, the cosine similarity, it's going to pick item 2 as more similar, because the angle between item 2 and the query item is smaller than the angle between item 1 and the query item. So here's kind of a concrete example of where Euclidean distance and cosine similarity disagree with each other. But that's fine. We couldn't really agree as humans either. But now I'm going to try to make an argument for why I think cosine similarity is better in general for this task of product recommendation. And so here's the thing. What is really the goal here? Like, as humans, we work for Amazon, we're trying to recommend this thing. Wouldn't it make sense to recommend items that are more popular in general? There's this extra factor here, which is, yeah, we want to show them something similar, but if no one likes this item, or no one rates it, or no one views it, or no one buys it, whatever our data set is based on, maybe we shouldn't recommend it as often. And if this thing is selling like hotcakes, this other thing, maybe we should recommend that thing more often. And going back up here, item 2 is more popular in the sense that Alice and Bob both like it and gave it 5 stars, and item 1 is less popular. And so maybe we should be taking that into account here. And maybe we should bias things towards recommending item 2. I should say, and I apologize for this being rushed, because I can tell that it is rushed. The fact that we treat the lack of rating as 0 is a very important choice with deep implications that we're kind of ignoring right now, because we're just treating 0 as a regular number, but it's really missing data. And there is a lot one could say about that that I'm just kind of ignoring. So I at least wanted to put that out there. Okay, so maybe it makes sense to recommend more popular items in general. And so if we had something like this, like a bigger vector means more popular here. So maybe we want to bias things towards item 2. And what I want to argue is that it's not a coincidence that cosine similarity picked the more popular item and Euclidean distance picked the less popular item. And that if you want to recommend more popular items, in this type of situation with a lot of zeros in your table, cosine similarity is going to have that kind of unexpected property that Euclidean distance won't. And so I have this big thing that from Piazza from last year that you can read over later. I'm not going to go through this right now, but I'll just leave it here as some notes for you. But I'll try to make a kind of intuitive argument about why this happens. And my intuitive argument about why this happens is there's lots and lots and lots of zeros in the data set. And so here in 2 dimensions, we can't really see the whole picture. This is really an arrow in like a million dimensions, which our brain can't really comprehend. But most of the numbers in these vectors are 0 because most users did not rate a given item. And so you kind of have these arrows pointing in all kinds of different directions. And because there's so many users that could rate an item, it's almost like every single arrow is pointing in a different direction because there's so many possible directions you could be pointing in. It's almost like every arrow is pointing in a different direction. And so a lot of these angles are actually very close to like 90 degrees in this space that's hard for us to conceptualize. And this is that very conceptual part that I said is hard to follow, but I'll try to make the argument. And so what happens then, it's kind of like all the arrows are pointing in different directions. And so if you have a big arrow, it's probably pointing in a different direction from your query. And so if two things are kind of pointing 90 degrees from each other, the bigger you make them, the farther away they actually are. And so in terms of Euclidean distance, the bigger you make this one here, the more popular you make it, you're actually making it farther and farther and farther away from your query item. And so Euclidean distance is not going to like a really big vector. It's going to say, oh, that's really far away. Euclidean distance would rather pick this tiny little unpopular vector that's actually very close to 0, because at least since they're all kind of pointing away from each other, at least it's not pointing that far away from me. And so by Euclidean distance, I'll actually prefer this smaller one that is closer to 0. Whereas if I look at angle, I don't have that effect. And so when I look at angle, the bigger ones are totally fine, and I end up recommending those. So there's a lot that goes into this. There's all kinds of issues of scaling that I'm not going to get into here. There are some cases where cosine similarity and Euclidean distance actually do give you the same answers if you scale, but we're not scaling. There's some reasons why we can't because of the sparse matrix. Long story short, there's much more we could go into here, but that was kind of my high-level hand-wavy argument. And it's okay if that didn't make sense, because being able to think in 700,000 dimensions was not really a prerequisite for this course. So that's okay. But I at least want to show you in the last minute that if I take this grill brush on Amazon and I look at the nearby items using cosine similarity versus Euclidean distance, and then I print out the total number of stars these items received, the Euclidean distance is recommending a couple more popular items, but then it's recommending these super unpopular items that only got 5 stars ever across all users, whereas cosine similarity is recommending a whole bunch of more popular items that have lots of stars in total. And so you're going to experience that same thing on your homework 6 next week, except you'll be doing it with word counts instead of products. Okay, we're out of time. I'll definitely need to make a note that this lecture was too packed. I did reshuffle a bunch of things between this class and next class. But anyways, oh, there's a question. I guess the big difference is that Euclidean distance cares about magnitude, whereas cosine similarity doesn't. That's exactly right. And there's some ways of dealing with that with scaling, but yeah, we're not going to go into that. So yeah, can we see some of these items? Sure, here's one of them. Oh gosh, a meat injector kit. Okay, some serious barbecuers here, some gloves. Anyways, we're out of time. I don't want to go over time, so let's stop here and we'll see you next week.